Hello. Oh, I guess Martin. Oh, there he is. I guess I get to do a few slides first and distract you. And Martin wanted to work on his slides a little bit more. But we taped down his computer. I think. I hope. So yeah, it's great to be on stage here. I finally made my way into a keynote. Sorry I haven't spoken before. I was busy making the compiler slower. So you don't mind? I keep doing that. It's no problem. Wow, you guys applauded so hard. The screen is shaking. So I'm really, really happy to start the presentation with this slide, and especially the next one. Last time we were here in 2014, I just had to look it up. We didn't really have an inkling that this was going to be on a slide a few years later, and here we are. And I guess the next slide really speaks for the previous one. The convergence, I think, is stunning for those of you who are project managers. It looks a lot alike. You'll see that 2015 dropped off because we feel confident that after 2.14 we can switch over to the 3.0 series of the language. While Martin was busy working on Dotty, we were on the evil corporate side working on the Scala 2 series, where basically the crossover of a lot of the Dotty stuff started happening in 2.12, where the function encoding, the trait encoding, the internal way of representing fields and traits and stuff like that were already aligned with the way that Dotty did it. And then we saw how that fared with Hotspot and tweaked some stuff in the encoding. So there's been this great dynamics already between the teams since 2016. In 2.13, as you know, and there will be talks about that tomorrow, we standardize on the new collections. Rumor is it that can build from wasn't your favorite thing. We vastly simplified it, and it's now called build from, I think. Go see Stefan's talk about how often it is used. The hint is not very often anymore, only really where you need it. So really, really happy with that simplification, really happy with the foundation for the standard library that is basically going to be the Scala 3 standard library as well. Go see Stefan's talk for more details about that. So the next phase of alignment, we're focusing on the compilers. So imagine taking these timelines and kind of, there's this zipper at the top, and you just kind of pull it down. That's what we've been doing all this time, and we're going to take the two backends are already the same. So the way that bytecode is emitted is the same already. And we're going to shift our gaze towards the middle end, where we have the two type checkers basically emitting tasty typed abstract syntax trees. Y. You'll have to ask Martin what the Y stands for. And so with that convergence, I think we're going to be in a really, really good spot to kick off the Scala 3 cycle. Then before we get to the main event, I won't speak for much longer. I have a compiler to make slower. Also really excited to announce that we're standardizing on the Apache license. You can read all about it. Thank you. Lawyers were wrangled. Blog posts were written, and let us know if somehow, those of you who weren't clapping, I see you, all of you. If you're not happy, let us know. This is not a done deal. Most of you have signed the CLA who've contributed, but maybe there's a few who don't have or have other legitimate objections. Let us know. There's our contact details are in the blog post. The other thing is that we're kicking off a hopefully annual tradition of developer surveys together with the Scala Center and NEPFL, Martin's team. We would really, really like to get your feedback on not just now in the hallway, but also let's record it with computers on the internet and collect results and incorporate those into our roadmaps. So we'll have this running for the next 2 months until after the next Scala days. It's about 25 questions, won't take too long, completely anonymous. But if you have any questions or come find me during the conference, send us an email. There's a thread also on Discourse if you have any concerns around it or just want to have a debate around it rather than just a monologue on the survey. So with that, very excited to switch over to Martin. Thank you very much.
Okay. So, thank you. Okay, so Adriaan has given you the roadmap, which was sort of the roadmap all along, and it's nice to see how well it has kept up. And at the end of that roadmap is Scala 3, which will be a major disruption, as people like to say in the startup scene. So if you do that, then the question, of course, is why? Why are we essentially changing the language to merit essentially a new super major number from 2 to 3? So I probably should explain why, for me personally, also that's something that I believe is really important. So because it has to do with the essence of Scala. So the essence of Scala, at least as far as I'm concerned, is the fusion of functional and object-oriented programming in a typed setting. The fusion has been done before with languages like Smalltalk, a little bit more object-oriented with functional elements, and CLOS, a little bit more functional with object-oriented elements, but it was all dynamically typed. And I think the first mainstream language that actually achieved that fusion was Scala, where I don't want to essentially ignore other languages that came before, such as OCaml, that tried that, but I think A, it wasn't as mainstream, and B, it was more an amalgamation. That means two languages side by side, and people use one or the other, and less a fusion, which is what I think Scala has tried and done. So the fusion, roughly, if you say, well, what part do I use for what? I guess every program uses both functions and objects, and generally functions tend to be used for essentially the logic of the program, and objects for the modularity. Objects are there to essentially outline the components of your program. So that's the essence. And then the question is, well, were we successful with that? And by at least one measure, we were immensely successful because I think that Scala was the first language that, starting from a statically typed object-oriented core language, we pioneered a lot of essentially new things that are now pretty commonplace, such as closures, function types, expression orientation. So no, essentially everything is, every statement returns a value. Tuples, local type inference, pattern matching, traits, lazy values, by name parameters. Then the x:/t syntax, yes, it existed before in Pascal and ML, but it was all but forgotten when Scala came up on the scene, and now it sort of has a revival, and a lot of new languages are doing the same. Dependent types, implicit parameters, and a lot more. So it's a lot of features, and we are, by now, in 2018, we're not alone. Many other languages have followed suit by adopting a subset of these features. I just mentioned C# adopted quite a lot of them, Kotlin, Swift, Java. Java is a latecomer, but every year it adopts one more feature so you could say, well, Scala, as it was conceived, is really where a large part of the industry is moving to. So in that sense, it's success. But it's maybe not an unqualified success, because I think that Scala also has quite its share of challenges, and there are still a lot of ways to essentially derail the project. And I think that if I talk about possible derailing the project, I would say that it typically comes from two sides, and both sides sort of see only some part of Scala and ignore the other. So one part would be to conceive Scala as nothing but a worse Haskell on the JVM. And the other side would be to conceive Scala as nothing but a better Java and ignore the deep parts. So both take one half of Scala features and ignore the synthesis. And I want to talk a little bit about either movement, either tendency. So on the functional side, there was the name Haskellator, which was coined by my former student, Sandro Stucki. So Haskellator means Scala is sort of the elevator towards Haskell. And for quite a few people, that's actually been true, which I don't think is bad at all. It's great. Haskell is a great programming language. And I don't want to at all to essentially diminish it in any way. But Scala, I believe, is not a very good basis for emulating all of Haskell's patterns. It simply isn't. It lacks. And I guess if you move to Haskell, you will feel that. There are certain things that are just much smoother in Haskell than they can ever be in Scala. So if you choose to ignore Scala's object-oriented parts, there's little point in using it at all. I mean, why not use Haskell or maybe one of the Haskell versions on the JVM? That's, I think, one part of it. The other part is better Java without Scala's deep parts, and that's where essentially a lot of other languages sort of jumped on the scene or slowly moved like tankers on the scene. So new languages such as Kotlin or Swift, and also, of course, improvements of existing languages such as C# and Java. So they generally, you see that they trade, I mean, they're moving in the same space, but trading abstraction and composition for more features, and I would probably lean out the window a little bit and say more ad hoc features. So one other thing that these languages do, which actually works pretty well, is that they avoid the more esoteric functional programming parts by making it less pleasant to express them. So that means that essentially you have less of a culture battle that you say in one team, well, how should we write our programs, this way or that way? In these languages, they clearly take a stand and they say, while it's possible to do some functional programming idioms, it's just not very pleasant. So it's not super recommended. Another thing that I believe that these languages promote is that by having a larger language, programs tend to be simplified because essentially there's more features that are sort of recipes that you can just mix and take up. Scala is often criticized for being an immense language, and that frustrates me a little bit because if you look at the data, it's absolutely not true. And I just show you the data. It's just one measure, but there are others as well. So here's the size of the language in lines of grammar size, so essentially number of syntax rules. You could also measure the number of keywords that would essentially give you fundamentally the same graph. So you see here's Scala. So it's more complex than Haskell, but that Haskell here is actually the base Haskell, Haskell 98, which nobody ever uses, and you would have to add the 85 actually language flags and language extensions that essentially to that graph, and I think then the bar would be quite a bit higher. And then over here you have sort of the other sort of industrial languages, Kotlin, Swift, Java 8, which are all quite a lot more complicated. And here you have C++ and here you have C#. For me, it was quite a surprise that C# is so big. It's even bigger than C++ if you do this measure. Even though I believe everybody will say C++ is a lot easier to use, harder to use than C#. So that means language size is not necessarily correlated with ease of use. It could actually be inversely correlated. And I think for Scala, we just have to be clear that essentially the language is actually not outrageously large. And furthermore, we will try to make it even simpler than it is now. But some of the patterns are hard to use. They're puzzlers, they're surprising behaviors. And again, that's something that we want to address. So the way forward. So I believe, and I think I should say we, which is not the royal we, but I and a lot of other people that I work with believe that Scala's fusion of functional and object-oriented programming is still the most promising way forward for general-purpose software development. But, there's a but, I think, but there are lots of things we have learned since the inception of Scala, including that the following: how to be pure without sacrificing simplicity and performance, how to do meta-programming safely, how to cut down on boilerplate for new idioms. And all these things, they are sort of things that we discovered and developed once the first version, the current version of Scala already was out. So because of all these discoveries, I think it is the right time to actually try to consolidate these and put them into a new version of the language. So that's the main reason why we think that Scala 3 is a logical and promising next step. So what we want to do is we want to incorporate these techniques in the language to make it simpler, more focused, and more pleasant to use. And in particular, what we want to do is we want to become more opinionated. So one aspect of Scala that was quite attractive for many, but quite a problem for others, is that it's really not just a language, it's a language toolbox. You could achieve a lot of things with essentially macros and macro paradise. You could really forge your own languages. And the problem, of course, with that is fragmentation, that essentially you have a lot of different dialects, and one dialect looks completely different to the next one, and people can't talk to each other, and they find essentially the thing stunningly complicated because they just don't understand the particular dialect. So we want to essentially reduce that and become more opinionated. We want to simplify. We want to eliminate inconsistencies and puzzlers. In fact, I have a close look at the puzzler book and say, well, essentially, how many of these can we eliminate in the next version of Scala? Would be great if we could eliminate a lot. Not that essentially a language can ever be puzzler-free. I think that's too much to wish for. That's not realistic, but we definitely can reduce them. We can build on strong foundations. Over the last years, essentially, many people have developed the foundations, in particular the dot calculus for dependent object types, which is an excellent guideline when it comes to essentially looking at the type soundness of the type system that essentially will be in Scala 3. And we want to consolidate language constructs to improve the language according to 4 dimensions. It should be more consistent, should be safer, should have better ergonomics, and be more performant. So I want to just give a quick rush through essentially the features just by mentioning them. We won't have time, and it would be boring to actually go in each one in detail. But to just say, well, what under these 4 points, what kind of things do I mean? So for consistency, to improve the orthogonality and eliminate restrictions, I would say definitely having intersection types instead of the width types in current Scala is a big advantage, because these intersection types, they have nice algebraic properties. In particular, they commute. So A and B is the same as B and A, which you would expect from an intersection, and which actually was not true for the previous width, where we essentially joined the compound types with the linearization of essentially class inheritance, which in retrospect was a bad idea. Once you have intersection types, it's logical you want the dual as well, and so that's union types. So Scala will have both intersections and unions. Then I put down implicit function types under consistency. Why would that be more consistent? Well, a method can have implicit parameters, right? So everybody uses methods with implicit parameters. So it's only logical that you say, well, once you lift a method to a function, then that you don't lose the implicitness. So you should have, essentially, functions should also be able to have implicit parameters, and you should be able to talk about that in the type. So this looks like just a little smoothing out, but it actually will turn out that that's actually the key to a lot of the progress that you can make in Scala 3. So this is sort of completely innocuous, but with enormous consequences, interestingly. The next thing is dependent function types. So it's the same thing. Methods can have results that depend on their parameter types. You want to lift that into the function space. And so that's also possible in Scala 3. You can have a function type like that takes an x of type A, and that returns an x dot b, where b is, for instance, a type element of the type A here. So that is essentially just saying that we want to lift these things into functions. And again, that's turns out that that's incredibly powerful, because that's just the products of dependent types that you have that way. Trait parameters. Classes could have parameters. Why not traits? Indeed, why not? Turned out that you had to sort of figure out the rules, what you do with diamond inheritance. So if essentially with the classes you have single inheritance, so then it's easy. But if you have 2 traits, let's say A and B, and they both inherit another trait C, then the question is who passes the parameters to this upper trait here. So that was the question. But once that's figured out, indeed, there's no reason not to have trait parameters, and they actually enable us to eliminate something which was pretty weird and ugly, called early definitions, which was just another way to essentially achieve some of the functionalities that you had with trait parameters. And finally, generic tuples. So, well, we have tuples, both tuple values and tuple types, of course, in Scala, but they went up to 22, and that was it, right? And they were each different, tuple 1, tuple 2, tuple 3, tuple 4, each completely different types. And that's, of course, why a lot of people said, well, tuples are no good, we should have H-lists, because H-lists, we can have actually programs that are generic in the length of this tuple, and that can essentially, it's much, much nicer to deal with. And indeed, that's true. But then the question is, once you have these H-lists, well, why keep tuples? And why essentially have this specialized syntax for tuples if it's just such a poor concept? So in Scala 3, actually, tuples are H-lists. So the tuple H, ABC, is essentially just a shorthand for writing, well, it's the H-list that starts with A and has on the right-hand side the tuple, alias H-list that has a B, and the third element is a C, and the H-nil would be the empty tuple. And so that's essentially the type theoretic expansion of these things. So everything you can do with H-lists, you will be able to do with tuples. The other thing is, in terms of representation, I think we can do better. We can essentially have a compact representation of these tuples up to a certain size where we don't essentially have these pairs of pairs things that H-lists imply. So that was consistency. What about ergonomics? So what's the reason for ergonomics? In fact, one thing is that we want to reduce boilerplate. Well, you say, well, I thought that's what Scala was all about, right? I mean, Scala came and reduced a lot of boilerplates in Java programs, case classes, no getters, no setters, no equality methods. Everything was provided for you. Great. But on the other hand, over the years, we have developed patterns in Scala programs that are actually quite boilerplatey themselves. So one, to stay with case classes, is we use case classes for data types left and right everywhere. And yeah, it's a lot more clunky than if you had an enum, not an ADT type. And furthermore, even for enums, well, we never had something like that directly, but now we have it. So we can write enum color, case red, green, blue. And that actually generalizes to things like lists and options and general case classes. You can use the same syntax for case classes with parameters as well. The next thing was type lambdas. So we never had type lambdas until somebody figured out, yeah, you can do it with some horrible contraption using structural types and type members and things like that, right? So this was so terrible that more sensible people immediately went and had a fancy macro system for kind projectors because they said, well, we just can't write that. But of course, it's for those who have to write that, it's super boilerplatey. And again, it's something where we said, well, that's something that essentially came up when we started Scala. We didn't even have higher kind of types. When we had higher kind of types, they weren't used that much. People used them more and more, and that was really essentially a sore thumb. So now Scala 3 will have type lambdas, so that's the syntax. So that's a type parameter. You can have several of them. They can have variances or bounds, and that's here is the right-hand side, which can be an arbitrary type that mentions the type variables. Okay, and the next aspect would be safety. So Scala generally is a fairly safe language, but there are some things where it could do better. So who among you has done a large refactoring of a Scala program where maybe you changed one type to another? Okay, how easy was that? Good? Well, for me, there was one sore thing. Normally, what I want is I just change the types, and the compiler gives me the type errors, I fix the type errors, I'm done. Except for equality. So equality is really the bad thing there, because I said, well, I compare two types that make sense, and now I change one to another type, and it just will always give me false, but at runtime. So that's essentially the one thing where, which is scary with large-scale refactorings. And actually, there was at least once in our compiler we didn't do a refactorings because we were scared of that. We said we just can't track all the points where we compare this type, the first type with the second type. So now we have with multiversal equality, which is essentially a nifty way to have essentially parts of things that can be compared to each other, but that can't be compared to things outside of their group. So essentially you can define groups of types that can be compared to each other, but not to other types. And you do that by essentially setting up implicits. And enums, of course, with the ADTs, every enum is its own island. So you can compare an enum only to itself, but not to other types. So that prevents you from essentially accidentally comparing a list of strings with a string, so that wouldn't make sense anymore. It would say, well, you can't do that. It's not a legal comparison. The next thing, restrict implicit conversions. I'm going to talk about that a little bit more. What we planned, what we don't have in the current version, Dotty, that's essentially the project name for Scala 3, but we will hopefully add it, is null safety, because it seems that's where the world is moving, and it's true that a Scala program doesn't use null a lot, but Scala programs don't live in a vacuum. They essentially have to interoperate with Java programs that can still pass a lot of null pointers, and I think that we should be able to tame that by putting it in the type. And we actually have a very good way to do that now, because essentially a nullable string is just a unit type of the string type and null. So in Scala 3, if you have a class type like string or list or whatever, it never includes null. So it's always null free, it's always pure. So if you want to add null, you have to write or null. And that's essentially for the interface with Java, what you do is that you say that if essentially you have a type and it doesn't have a not null annotation, then essentially the import of the type implicitly adds the or null in order to stay honest and add that to the Java type. And finally, effect capabilities is something that is a little bit further out and has to do with essentially, again, implicit function types and the way to handle purity. Performance. There are some parts in Scala where we could do better in making abstractions cheaper. So Scala is generally a language which encourages abstractions. And it would be nice if abstraction, we didn't have to pay a price for abstraction, but sometimes you do. So the first thing is you want to introduce essentially an opaque type. So essentially a type that is implemented as some other type, but you don't know what it is. So previously we had value classes for that. So you could say you could define a new class like meter, and it takes a double, but a meter is not a double. So they're two different things. The problem with that is that value classes don't guarantee no boxing. They guarantee that no boxing as long as essentially you see them monomorphically. You have the type of the value class, but that stops once you put them in a collection, or worse, even once you put them into an array. So arrays over essentially value classes can be very inefficient, because every time you put it in the array, you have to box, and every time you pull it out of the array, you have to unbox. So opaque types don't have that disadvantage. An opaque type just says, well, A equals B, so that's my implementation, but you as a programmer are not allowed to know that. So essentially a type checker will complain if you use a B as an A. And essentially there's in the companion object of A, that's the only space where you actually can know that A equals B, and where you then can define the appropriate conversions and operations on these types. So that hopefully is essentially the same, very close to what value classes are, but without the boxing penalty, with guaranteed non-boxing. The other thing that we have is erased parameters, which is again something fairly simple and obvious. So in Scala you have quite a lot of things typically implicit, so I should have written implicit here, that you pass a parameter and you really need that implicit parameter only for the types. So for instance, sometimes you want to call a method only if some type expression A is equal to a type expression B. And we do that with an implicit, so equals colon equals, and you can just essentially pass the evidence. But afterwards, at runtime, you might not need it anymore. So you can maybe arrange things that you don't need it anymore. So if you don't need it anymore, then you can put erased on the parameter, and that just means, okay, don't bother with generating code for this. So essentially, this is just to make the type inferencer happy and the type checker happy. Afterwards, you can drop it. And in fact, we drop it very, very quickly, so immediately, even during type checking, so we might need to generate a very, very large term as evidence. Sometimes these evidences are complicated, but essentially once we have done that, we throw it immediately away and essentially just give you essentially the evidence of that. So that hopefully will not only save runtime, but also cut down on compile times for these sometimes very hairy type level parameters. Okay, so that's essentially a quick tour, whirlwind tour through the features that we add. We also remove quite a lot. So here's all the things that we removed. Well, a short list. There's some more. There are no more existential types, so use dependent types for that. There's no procedure syntax. Use equals for that. There are no early initializers. Use trait parameters. XML literals in the language are gone. They're now in the library. There's no limit 22, so that's a simplification. Everything can go up to any arbitrary arities. For tuples, you've seen we do that by mapping tuples to H lists, and for functions, we do that by essentially having a function XXL, which essentially takes arbitrary number of arguments in an array. There's no automatic unit insertion. We will be a lot more picky about essentially when you insert, that you cannot simply drop the unit when a function takes a unit parameter, then you're supposed to pass it. There's no weak conformance, which was something fairly esoteric, but it could trip you up. We planned on removing both auto-tupling and multi-parameter infix operations, which actually are related, so that essentially should make a lot of the conversion rules less surprising. Good. But the biggest, if I should say, among all this feature list, if I should take out one of the parts that I think is the most important, then it's really the improvements to implicits. Implicits actually turned out to be where Scala innovated most. It wasn't so much there at its inception, but it was during the development of Scala in one version after the other. Essentially, implicits got a lot of refinements. So first for type inference, then for things like implicit classes, things like context bounds. All of these were essentially added over the years that Scala existed. And I believe that implicits can be both a blessing and a curse, and the goal for Scala 3 is fewer curses. So simplify and avoid traps. One part where we actually work out essentially the theory of these new implicits, which is actually very pleasingly simple, is the paper is called Simplicitly, and it appeared in January at Popper this year. So in a nutshell, what we want to do with implicits is that the first thing we want to do is that previously we had both implicit conversions and implicit parameters. And if you look at code, then often it was sort of a roughly comparable balance. You had programs used quite a lot of implicit conversions, and they used quite a lot of implicit parameters. In fact, it's a historical accident. Implicit conversions came actually first, because they were essentially invented as a way that we could implement an interface by existing classes without touching these classes. So there's this problem that you say, well, I have a class, and then somebody else invents a new interface like ordered. And I say, well, this class is ordered, so I want to make this class ordered, but of course I can't without touching the class and inheriting ordered. So that's why we had implicit conversions to solve this problem. So nowadays we would say, well, that's stupid. Do a type class, or you don't do an interface. But at the time it was less well known. In fact, type classes came afterwards as sort of a natural generalization of implicit conversions to implicit parameters, and then implicit parameters were invented to model type classes. So that's what the history was. So implicit conversions were in Scala since the beginning, since about 2004, and implicit parameters came maybe 2 years later. And so even to this day, if somebody writes an implicit conversion, implicit tutorial, often they will start with implicit conversions and say, yeah, you want to know about implicits, here's this conversion from here to there. And it makes me cringe, because now I see this is usually it's a terrible idea to propose what these tutorials often propose as a first step. So what I want to achieve in the future is that implicit conversion is a lot smaller. There will probably still be some uses, but we really want to discourage that, and we really want to put ways that enable you to use way less implicit conversions than now. And that, by contrast, implicit parameters will be a lot more important. So how do we cut down on implicit conversions? Well, the first is that a lot of the implicit conversion use cases, we can come up with other abstractions that are actually more natural for that. So what does this class here at the bottom do? It's an implicit class, CircleOps, takes a circle, extends anyval, and does this thing here. Well, that's just to set up an extension method, right? So you want to have a method, circumference on circles. You haven't defined it in your circle case class here. So that's a way to do it. But it's a very roundabout way. This is boilerplatey, right? I mean, we were against boilerplate, but now there's a lot of boilerplate introduced here as well. In particular, since it's a pattern that I guess is pretty common. So you do this over and over and over again, and it's heavy. So what we want in the future is something that is much clearer, in a sense that we say, well, we have an extension, we call it CircleOps, and it's an extension for circle, and then we just write the method as it is. So this is implied that this is a circle, so if we mention radius, then essentially that's the radius for the circle here. And you can have essentially all these extensions for extension methods, and also for what Rust calls trait implementations. So this thing for me was inspired from Rust, that's where I saw it, but I looked it up since, and I saw that Swift actually has something very similar, and they even use extension for it. So it's not something that is unique to Scala, but I think in Scala we can use that to actually cut down on implicit conversion use cases. We can say in a lot of situations it's actually clearer to express it like that. Okay. The next thing we want to do is we want to actually actively prevent you from writing implicit conversions. And the way we do that is with language imports. So previously, if you wanted to write an implicit conversion, you had to import language implicit conversions, right? Unfortunately, for me, that's all too easy to do, in particular if you're an IntelliJ user, because IntelliJ will just do it for you, which I think is a terrible idea. That's the point of requiring these language imports is to make you think. And you cannot think if the IDE does it for you under the covers. So you really should type this out, and it's an appeal to the folks at IntelliJ to actually exempt language imports from all this fancy auto-importation magic. They're not done for that. But anyway, even so, it still wasn't enough, because you had a bright library designer who comes away convinced that it's a great idea to have a conversion from strings to int, like this one here, string to int. And then he puts it in his library, and once you import it in one way, you have it as well, without maybe even realizing it. And that's, of course, is then the big mess starts. You have these conversions, and you don't know what they do. So it's wrong to appeal to library designers to say, don't write implicit conversions, and if yes, you have to put this auto import in here, or this language import, because it's just too easy to do so. And maybe I don't expect that people here in this audience will think that string to int is a good idea, but there are lots of gray zones. There are lots of things that people think it's a good idea, and in the end it's not. And I must say I know that because I have gone through this cycle many, many times where I thought an implicit conversion was a great idea, and in this case we can do it, and then in the end I've come to regret it. So we all have to collectively be protected, but what's even more, not just the library designers, even more so the users, because the users of these libraries, they will have the problem if the implicit conversions happen. So what we will require in the future is not just at the point of definition, but also at the point of use. If there's an implicit conversion that the compiler inserts here, then you will need a language import. And the good thing is, if you don't write a language import, the compiler will give you essentially an error and say, no, you can't do that. So it's an excellent way to actually figure out where essentially these implicit conversions are happening. Just don't import language implicit conversions, and the compiler will tell you. Okay, so there's one exemption, which is that it turned out that once we ran it, that if a conversion is actually defined together with its target type, then that's typically a thing that is easy to control and is a good thing to do. So these are exempted, but for the others, you have to essentially write the import. Okay, so what about the other side of the coin, making implicit parameters more useful? So there are a number of improvements in the works. So the first one is, so far, implicit parameters always had to come last in a function, and that we will actually drop this restriction, so they can come in any order, and there can be several of them. Why is that important? Well, it's important, for instance, if this type B here depends on the first variable x. If you have a dependent type, then currently you're out of luck. You have to use the infamous aux pattern or something like that to actually get there. And it's one of these hoops that I don't think that ideally you shouldn't have to jump through. So we can get there by essentially having multiple implicit clauses. But wait, you say that there's an issue now, because if I have this pattern, with the implicit first and then the thing here, and then if I pass f a parameter, how do I know it's the implicit parameter or the other? Because we said, well, if a parameter is given, then if it's explicitly given, then pass it. If not, then infer an implicit argument. So again, the new requirement is that if you pass a parameter to an argument to an implicit parameter, you have to use explicitly. So explicitly is essentially a magic method that says, well, I want to essentially give you something explicitly for this implicit parameter. And that essentially enables the other thing. And I believe it's also much clearer, because now you actually know whether the argument is for your implicit parameter or it isn't. You could get confused even before, even with the implicit arguments always coming last, because of apply. So if you have a thing with an apply method, then you don't know whether you insert the apply and then call it, or whether it's the other way around. And finally, there's implicit function types, which give you essentially the purity without sacrificing simplicity and performance. Unfortunately, I won't have time here to actually show you that. If you had a little bit more time, then I would run you through a way to do that. So I just put up the slide and say, well, there's a lot of things you can do. In particular, things like dependency injection, things like effects, where implicit function types are a great alternative to in particular, the existing approaches using monads or monad transformer stacks, because fundamentally they compose. So essentially, if you have an implicit function type that takes x and then one that takes y, they can come in any order, and you can take a subset. And none of that requires any plumbing. All of that is done completely transparently by the compiler. So that's basically the reason why implicit function types is so much nicer to use than monads and monad transformers for these kind of things. Again, we're not the first to have discovered that. There's a movement gaining steam, I think, called algebraic effects, which is basically the same observation, that if you say, if you have effects, then you want to have a system where your effects compose naturally. And implicit function types is, I believe, the simplest way possible to express simple algebraic effects. For more complicated algebraic effects, you would need continuations, which is another question. Okay, so that was a quick rundown to the language, but the language in isolation is of course useless, so you need tooling. So what do we have so far with tooling? Well, we have a new compiler. It's called .c. So .t is essentially the project name derived from dot, the calculus, and .c is the compiler for it. We have actually pretty good IDE support already through the language server protocol, and it's supported directly by VS Code, but hopefully in the future by other clients as well. We have a REPL and a doc tool. And most of the tooling is built around Tasty. So I want to talk a little bit around Tasty because it's also important for the interop. So Tasty stands for Typed Abstract Syntax Trees. So an abstract syntax tree is essentially the internal version that a compiler uses to understand the program, and after the type checker, they're all typed, and essentially that's what typically the compiler wants to see, and how it conceptualizes what's in a program. And we use Tasty for a lot of different things. So for us, these typed abstract syntax trees are the standard serialization format for Scala. So it's how we represent essentially what's in a Scala file, so that when we do separate compilation, the compiler understands what's in other modules, and also in the future, how we can generate code from Scala, complete code. It has the complete type information, including all implicits are made explicit in that format, and it also has the complete position information. So that means you can use that very nicely also in an IDE, in an editor, because it really literally tells you everything you need to know about the program without any information loss. And at the same time, it's actually surprisingly compact. So we worked really hard to make this compact. So that's basically the whole optimization exercise is how compact can you make this? So in the end, it's about the same size as source, which means it's actually cheap enough to generate this as essentially the standard pickle information that we have for Scala programs. So in fact, that's the only thing that we generate when we do pickle information between Scala modules. So the vision of Tasty then is that you have essentially a single format which is used for a lot of different ways. So the first one is it's used as I said, as to support separate compilation of Scala 3 programs, now .t programs. So essentially Scala 3, when you compile a Scala 3 program, it generates Tasty, and when you want to know what's in a different library file or something like that, then you consult the Tasty and find out what members it has, at what types, and so on. What we have as a proof of concept, Guillaume Matres did that, is that you can actually also do that at quite reasonable overhead and work to map current Scala into the same format. And we don't have that yet, but we plan to essentially have the round trip as well, so that we can essentially take Tasty and understand Tasty from the current Scala 2 compiler. So that's important, because once that's done, these two parts can talk to each other. So right now, essentially, Scala 3 can understand Scala 2 because it has another mode where it understands the Scala 2 pickling format, but it doesn't work the other way around because Scala 2 doesn't understand Tasty. But once it does understand Tasty, it can actually figure out what's in a Scala 3 file. We use it for the IDE with LSP. So if you want to find references or something in a program, then essentially you look in the trees, or at least you look in those trees that actually mention the name, and that lets you find all the references at actually very, very good speed. And we use it to generate, well, we can use it to generate class files. So that's currently essentially just for testing purposes. We don't have the tooling set up to do this, but it works in the test suite that we say we take these Tasty trees and we generate Java class files. And why is that important? Well, it's important because we are no longer then tied to generate only one kind of class files. Once we have a tasty class file generator, we can generate Java 8 class files or Java 11 class files, it doesn't matter, or Java 14 class files or whatever. And we can generate JavaScript files, and we can generate native files. So this is a great way to actually get cross-building to work. Caveat, of course, sometimes you need to have essentially sources that are platform dependent, maybe different types, different implicits and things like that. And then, of course, we can't do magic, and the single tasty thing will not do that. But in many other cases where this is not the case, we should be able to do that very well. And finally, this tasty thing, because it's essentially standardized, it's essentially the new platform, it's the serialization format, it's also a great way to essentially put additional tooling on that. Like macros. Macros can essentially take trees as defined by tasty, produce other trees, or analyzers, or optimizers, or other things. Okay, so there are lots of use cases for this tasty thing: separate compilation, IDEs, macros, cross-building. And that brings me to the final point of this talk, which is meta-programming. So when I talked about essentially all the new features, then there's one sticky point to say, well, yeah, what happens with macros? That's, I guess, on a lot of people's mind, because macros so far are very much tied to the current Scala compiler, which will go away, NSC. So def macros is just a thin veneer around NSC, and macro paradise is basically the same thing. So they basically go into NSC into the current Scala compiler for everything they do, and that wouldn't be a problem by itself, but they also expose a lot of the internals of the current Scala compiler. Owner chains and differences between typed and untyped trees. It gets rather tricky and hairy and confusing a lot of the times, and that's because it essentially just throws open the implementation of the current Scala compiler. There's another macro system that doesn't, meta programming system that doesn't have that problem, which is called Scala Meta, but that has a slightly different use case. So that's really external tools that analyze and transform programs. So essentially, they would have a thing which is essentially not inside your compiler, but a thing that exists separately, that essentially you can essentially query a lot of programs or populate a database or things like that. So that's a different use case, and one which will not go away. So Scala Meta is completely independent to what we want to do with meta programming in Scala 3. So what do we want to do? So what we are going to do is what I call principled meta-programming, where we say, let's be very simple. Let's just have essentially two fundamental operators and then another two. So the first operator is called quote. And it takes an arbitrary expression, and it gives you the code for that expression, so as a data structure. And the dual of that is splice. It takes the code of the data structure and puts it inside another quote. It splices it inside another quote. And if you run the splice at the top level, that means that you run a macro. So because it means, well, here's some code at the top level, it means, well, run that code and produce essentially what the final result. So to do that, then essentially the other two operators are inline and run. So what inline does is, as the name implies, it just moves something from the definition side to the use side. So macro expansion would then be move the macro to where it's used and then run it, and that will expand it. So that's essentially two steps. Splice and inline is the macro expansion. If you combine those two with run, then you get staging. That means runtime, code generation at runtime. So that's essentially the two different parts of it. Okay, so if we look at the diagram here, then we have normal code, which has type T, int, string, whatever, and then these trees, these code parts, they are called expression of T. So that's essentially the code that essentially is the code that, when you integrate it in a program, will eventually produce a T. And as I said, quote goes from T to expression of T, and splice goes from expression of T to T. And that is super principled and very nice, and you can do lots of things, but it's also super restrictive compared to what we currently have, because one of the things you can't do is look inside one of your trees. This expression, it's a black box. It's just a code of type T. You can't look inside it. And so what we want to do is augment that by essentially having another part to this and say, well, these code expressions, in the end, what are they? They're just typed abstract syntax trees. That's what the compiler sees. And then the question is, well, how do we expose them? And in the end, we just says, well, we have a perfectly good format, and we have standardized it. It's called tasty. So let's expose it as tasty trees, because that is not a compiler, it's a serialization format. It's something that we will actually have to keep stable over many, many versions, because it's the way that Scala programs will talk to each other. So there will be essentially two other operations, reflect and reify, that I call that map and black box, a code of type T to the underlying tasty tree, and from the tasty tree to the expression tree. Okay, so that essentially completes this tasty vision that we say, well, we have tasty sort of sitting in the middle, and macros will become very, very powerful, because they are just at the center of it all. So they can take all this code and convert it, and furthermore, they can do so and even look at other compilation modules, because at the tasty thing, that's also the point where we essentially pull in modules of different files together. But there's one restriction, and that's that in order to do that, you're restricted to so-called black box macros. So here I should say, well, the way this is done is, so here on the left, you have essentially the type checker that checks your programs, and then pretty immediately afterwards, it essentially generates this tasty thing. And from tasty, you go with essentially all the transforms, the middle end, and from there you go into the back end. So if macros work on tasty, they get expanded after type checking. And that means that programs must type check before macros are expanded. So you can't have an incorrect program that sort of gets healed by macro expansion. Macros always work on type trees, so it's impossible. It doesn't even enter the system that you would have an untyped tree and run a typer on that or things like that. It just doesn't exist in this world. It also means they're hygienic by definition, and I believe it drastically reduces the number of things that can go wrong. On the other hand, there are certain macros where you say, well, that is actually not enough. My macros actually need more than that. They have to essentially expose the types and change the types. And our answer to that is essentially language level solutions. So if something is really important and affects the types, then I believe that it is a good place to put that in the language. And we have done that already with a number of things. One was the lazy macros for implicits. It's quite ingenious, but also super fragile. So that's actually now in the language. Type lambdas I've mentioned. They essentially replace or make kind projector to a large degree redundant. Context injections, so macros that sort of just add an implicit to things. Implicit function types are a great alternative for that. And we have still work to do, and we count also on your feedback and your help with that. One thing I believe we absolutely must do is some way to do type class derivation. So I think the time is ripe to actually add that. And then another thing I really also would love to do is type level functions. So essentially computed functions that do some computations to give you a type. Okay, so migration. I've thrown a lot of concepts and stuff at you, and new language features, removed language features. How are we ever going to migrate to this Fata Morgana, the new world? Just stay calm, and because despite many differences, I think Scala 2 and 3 are still fundamentally the same language. And more specifically, there's a very, very large common subset which is perfectly workable where they are actually source compatible. So that means if you want to migrate, then there's a will be there's a large subset which actually we will have a mode in the compiler to figure out, to tell you that you're in that subset, where you say, well, this thing will compile under Scala 2 and it will compile under Scala 3 and it will produce the same result. So that's number one. Second, we have actually rewrite tools so that they can handle much of the rest. So the compiler has a rewrite mode where it can essentially figure out what was meant in Scala 2 and give you the Scala 3 equivalent. And Scala Fix is also a tool that nicely shapes up with that purpose. So I believe that despite what many people fear, that the situation is actually better than for Python 2 versus 3, because mostly because of static typing, which enables these rewrite tools. And secondly, also because unlike Python, we actually have binary compatibility as well as source compatibility to play with. So now you say binary compatibility, wait, wasn't that just the Achilles heel of Scala? Wasn't that every time where essentially that's much harder than source? So I mentioned binary compatibility as an advantage. Well, actually, yes, because what we have today is actually that Dotty can link with Scala 2.12 class files. So it means it works with the Scala 2.12 compiled standard library or any other library, really. We can just read it and work with it, which is actually much better than Scala 2.12 to 2.11, say. You can't do that with a 2.11 library pulled in with a 2.12 compiler. So we have today a Dotty module that can sit just on Scala 2 modules, so that means we can interoperate, we can have systems that gradually migrate to Scala 3, but that still rest on a Scala 2 basis. But it's still very restrictive because it means before you can Scala 3ify anything, all its dependencies have to be Scala 3 under the current thing. But with Tasty, actually, we believe we can change that as well. Because using Tasty as a common intermediate format will not only help us share a large part of the compiler structure, the whole middle end and back end already between the Scala 2 and 3 compilers, but it also gives us two-way compatibility. So in the future, you should be able to freely mix and match anyway your dependencies, and I think that will be a big help in the migration. So roadmap. When is this going to happen? So 2020, what's going to happen until then? So we are in 2018. We currently have Dotty 0.9, 0.8 I think is the last released ones. There's a new one every 6 weeks. So essentially we have rolling Dotty releases. And the purpose of those is to flesh out the design. I've said there's some things still to be designed, get feedback from the community, and essentially do iterative refinements. We plan to go into feature freeze about a year from now. So hopefully by Scala Days next year, we are in feature freeze. And then we plan to use another year for essentially stabilization and get the ecosystem across. So that means there will be Scala 3 developer previews, which will essentially be bug fixes and tooling improvements, and hopefully with every review there will be a larger part of the Scala ecosystem that will be on Scala 3. So that's my hope. And then maybe by Scala Days in 2 years from now, we will actually be able to announce Scala 3. The other barrier is, of course, stability. It's a new compiler code base that makes me nervous. That should make you nervous as well. So we try to mitigate that by essentially running the same tests. So most Scala 2 regression tests are in the Scala 3 test suite. We are slowly building up a community build for core libraries and tools. What's holding us back here is mostly macros right now, that essentially, since we can't do the Scala 2 macros, it turns out that macros are transitive dependencies of almost 100% of the ecosystem in Scala by now. So what we really need to do is we need to have an alternative solution, and then we have to work with the low-level libraries that write these macros to have essentially versions out for Scala 3. The good part is that since they are based on Tasty, the new ones, they will work for Scala 2 as well. So once Scala 2 is on Tasty, you will have macros that can actually work on both 2 and 3. And the other thing, what we do is we do bootstrap. So we use our own compiler to compile everything we write, but we don't bootstrap from essentially a Scala 3 code base. So everything gets compiled with a Scala 2 compiler and then goes gets compiled again with a Scala 3 compiler that we know that that works. So what we plan to do then in the remaining time until Scala 3 is ensure that core projects are published for Scala 3, and long before that, we probably in the next weeks or something like that, we want to use our own compiler as the bootstrap root. So essentially start with an old version of the of our own compiler. Why does that matter? Because then finally we can eat our own dog food. We're not forced, we can, which will be a great joy to be able to use all these fancy Scala 3 features in our own tools. And that, of course, we can't do right now because the first step is still Scala 2 for the compilation. So you can try it out today. .eepfl.ch has rolling releases every 6 weeks. If you have questions, suggestions, or concerns, then I imagine quite a few of you will have one. Then talk to us anytime around the conference or after. There's a panel at the last day of the conference where we'll respond to questions, but of course, catch me before that if you have something that you want to discuss. And also, there's a contributors workshop on Friday, I think on the Zalando premises, that I believe still has some number of places, 8 or so. So talk to Heather Miller if you want to go there. Thank you.